All right, we're back on track for time, so we're just gonna kick straight into the next session, which is Gabriel Dos Reis, who's going to be telling us about program representation in C++. Hey, Gabby, how are you doing?
Oh, hello, Sai. I'm good. How about you?
Good, yeah, excited for final session of the day so I can go get some food. I haven't eaten yet. It's like,
Yeah,
it's
I
usually my
also
dinner
need,
time.
I agree. I also need breakfast.
Yeah, it's like 20 past 5 my time, but morning for you. So,
Okay.
all right, take it away.
Okay. Hello, everybody. I'm Gabriel Dustreis. I'm architect for Visual C++ at Microsoft, working on C++ compilers and tools for systems programming. Today, I wanted to share some of my thoughts on persistent representation of C++ for fun and profits. What am I actually talking about? Um, I'm talking about the idea of making it easy for all C++ developers to have access to the same representation of C++ programs that their compiler have, and have this being done by the community and the facilities developed over this developed by the community. And part of why what this project for the community is that when we take C++20, which came with a lot of bunch of new features, one of them is modules. The conventional way that C++ compilers implement modules is that they work to build a very nice, complete, semantically complete representation of your module's interface. They save it on disk, and when you import a module later, they just load that in memory and then merely go by their job. And when they're done, they just throw that away, kind of waste. And the other thing is that if you really want to use C++ to its fullest extent, you really want to have access to the highest levels of abstraction. You do not want something like extern C something something. You want the template, the concept, the context, function bodies. You want to compose those things, right? So how do I get there? Well, the idea is, well, C++ is a very complicated language. Everybody will tell you that. But it's not impossible. The way you get there is that you aim for something that is general, more regular, general enough to contain all the barnacles of C++ inside. And then you have that semantics, driven and implemented, developed, driven by the community. That's the goal. So the problems with the static quo, as I was saying earlier, is that you have these interfaces for C++. It's a language that is really beautiful in the sense that it has zero overhead abstraction. It allows you to have light with elegant abstractions. And when we build all those things, the next thing we do when we want to talk to another language is we say extern C, which is that we drop right away down to the lowest levels, the ugliest parts, and that's how we communicate with our language. We need to change that. If you have this high level representation, you can change that, and I'll show you how we can get that done. The other thing is that worries me is that because we do not have a community shared common representation, we have some form of fragmentation. Each compiler vendor would lock in their own solutions, and it becomes difficult to talk to someone like have code that's working on Windows, want to compile the same thing on Linux or Mac, and it communicates between the libraries, for example. And on Windows, for example, I have 3 or 4 compilers, and it's really a shame if we will have to deal with end format for end compilers, each going by their own way. And this is already a problem for people who are building and shipping modules. And the last thing I want to say is, even though we write C++ programs as sequence of characters, and then we read these things, for automated transformation, that's not really the best representation. We can do better, and that's what I'm trying to rectify. So the central notion about this representation stems from something that C++ compilers have been doing, especially C++ 20, which is what we call module interface build artifact. When you compile an module interface, the compiler generates something that contains all the information that it needs to process name lookup, constant evaluation, template instantiation, all that kind of stuff. And then the idea is to reuse that artifact that in many cases will be thrown away. Like it is a notion of waste that we need to get well handled on. We need to be more into green computing with C++. So these artifacts are reused by the compiler, and the compiler knows them. The compiler really takes advantage of your hard labor. Like you work very hard to write your program, organize everything. Compiler look at it and then takes that advantage of it. Concretely, here, taking an example, the MSVC toolset, but the GCC toolset, client toolsets, quite similar in structure. So imagine that I have the interface file, right? This is IXX, and then I have an implementation file of module, which is CXX file. When I compile that, usually it would generate a compilation step, would generate a bunch of object files, and then I can link them and produce either an executable, or I can get a shared library, either .so, .dilib, or DLL. But at the same time that those interface files are being compiled, the compiler also produces this metadata with the MSVC compiler. It is .ifc file. GCC will be what they call CMI, which is compile module interface. And if you Clang, it is PCM file. But essentially, it contains a high level, a very structured representation of your module interface. It's a module interface or header units and of those structured PCHs. Now, the nice thing about the IFC file, the BMI, whatever you want to call it, is that they offer the exact same semantic content as the original input source file. That's just a sequence of characters. However, if you understand how that structured data is saved on disk, you no longer need a C++ compiler to actually process it. So you don't need to know anything about name lookup. You don't need to know anything about the resolution or that kind of stuff. You can just write your Python script or TypeScript scripts or whatever scripting language you use, and just go and merely plot through that file and get the same and enjoy the same benefits as your compiler does when it processes your C++ file. And by doing that, now you see that we kind of like democratizing, giving the masses, everybody, the same access to those data, that high-level semantic representation as the compiler. And the interesting thing is that once you're able to process this metadata file, you can generate anything that you want. You can generate introspection, like at build time. You can generate new source files out of it, or you can even, you can save that file. At runtime, have your program open that file and then act upon its content, right? If you want to provide a type-safe linking or computation, like marshalling data and send it over network to different machine, and that different machine understand how things are, was byte, for example, they are doubles or they are long integers that are part of a structure, and unique pointer, that kind of stuff. Just being able to get the actual representation, how it is done, and the description of it allows you to automatically generate code that bridge the gap. This is really a enabling technology for the C++ community, and it would be a shame to let it go to waste. So in short, while your compiler is benefiting from your hard labor, you too can benefit from Syllabur, right? So, like you said earlier, you know when you compile, you produce these IFC files. You can use those IFC files if you understand the structure. You can generate new C++ files that are compiled and linked into your program, or you can generate resource files that are compiled to do something else, or you can just generate some monitoring program so you can do some kind of introspection. This is new. This is powerful. Okay, but to get there, you really need to make sure your C++ tool vendor is not hiding the structural information of these metadata from you. If they are, please tell them they shouldn't. They should stop. They should tell you what they look like. Okay. So to get there, to get that structure of the binary representation, and for it to scale, to the places where C++ is used, you need a complete representation. You need something that's very efficient to process, and to avoid vendor lock-ins, or at least to minimize it, you want a representation that is compiler neutral. So it's very ambitious, and people will tell you it is impossible. Well, it's easier to say something impossible than to actually get in and make it happen. And I want us not to take the easiest path, but actually make it happen, because the reward is greater than just denying and basking in laziness. So to have this representation, when say compiler neutral, people say, well, do you mean that we have to take the union of all the compilers on the planet and then put all that things in a big spec? That will be unmanageable, and that will be true. But that is not the only way to go about it, right? Like you said, we can find a more general representation framework in which we can express all of these variants, and that is possible. And that's what I want to talk about. To get there, it requires engineering and science, right? So I'm talking about the engineering choices that I made during this project. The first thing is to abstract away from concrete syntax. So what I mean by concrete syntax is all these grammar productions that go around. But what you want is you want a mapping from the concrete syntax to the semantics resolution, and make sure that the semantics capture absolutely everything. And then you have a way to go from that mapping is you can reverse back to the concrete syntax. And again, you have to focus on the semantics, really the semantics, not the syntax. C++ has too many ways, for example, of initializing variables. Most of them differ very little by syntax. What you want is to capture the semantics so you can reduce the complexity. The ISO standards has drawn a lot of barnacles, right? And there's a bunch of irregularities. You do not want a representation that faithfully mimic those structures irregularities. You want something general in which you can express restrictions enough that reflect those irregularities, but you don't want a representation that itself is so ugly, is so tortuous. Okay, and then in that framework, you need to have a way to represent vendor extensions, because, well, let's face it, in real world code, you all have extensions, and that's the way things are. When you look at, I was saying earlier, don't focus on syntax. When you look at the ISO grammar, this is count that I made, a couple of weeks ago. Well, I have about 348 production, non-terminal production, and I'm not counting the size of each production, I'm just counting the non-terminals. Right? Okay, it's about 350. And it keeps changing. When the structure of them keep, every time that the C++ committee meets, there is a high risk that these rules or grammars will change in form or in some sense. Okay, so we cannot use that as the basis for this simpler representation. We have to move to something else, which is the simplicity, the generality, the regularity, and remember that when we talk about semantics, the best way that we know in computing to represent semantics is to rely heavily on types, because types are the best approximation that we have for runtime semantics. And we know we can make it minimal. It is very important that we have this representation as minimal as possible for people to be able to navigate, to deal with them in practice. And like I said earlier, compiler neutrality is really important, because we want these representations across our platform, all compilers. And of course, we want to be able to scale this. Like, I'm traveling and then have only my laptop. I should be able to handle hundreds of thousands of lines of code on my laptop during a long flight. So, must be very efficient. To get this on disk, persistent on disk representation, I took a lot of inspiration from work that I did with Janus Strastrup about 15 years ago or more, and it was called the IPR, which is internal program representation, very imaginative naming. So the idea with the IPR is that we have class hierarchies, we have templates to capture commonalities, and then we have interface that separates. Like, when I say interface, I mean pure virtual functions, abstract classes so that can separate the real interface and the ugly implementations. And the ugly implementations can evolve, but if the consumers only take dependency on interface that are relatively stable, you can have wider adoption, can apply the framework to much wider scenarios and over a longer period of time. Now, when you're writing something on disk, you don't have vtable. Like, class hierarchies, they just essentially mean vtable, and then you overwrite stuff. But you don't have that when you're writing on disk. All you have access to is some kind of switch statement, tag, or whatever it is. But if you take a step back from that low-level view of representation, like, what is it really we're trying to do? You realize that, well, we are trying to describe data structures in a principled way, and the go-to field for that is universal algebra or multi-sorted algebra to surface commonalities. And then you're going to have a bunch of types, things, but most of them will share some structure commonalities, and then you apply the principle, the generic programming principle by Alex Stepanov called gradual lifting. Just you start from something very concrete, very concrete situations, and you try to literally, gradually try to find commonalities, and so they can have something more generic that when you instance it back, you get exactly the same scenarios that you started with. And, this is engineering, so you'll have to exercise some taste and common sense. So when, doing that concretely with the MSVC toolset means that I started with the Microsoft compiler. It could have been GCC, it could have been Clang, but in the last 8 years, I've been mostly working on the MSVC compiler. That's the thing that I had. And then start abstracting over details. Remember, I want compiler neutrality. So you need to abstract over implementation details, over specific compiler ugliness. And slowly abstract over and make sure that you can instantiate these things with other compilers. And you get something that's quite useful, beautiful. So those 3 steps, I think, are the essential keys to this project. I've already done part 1 and a bit of part 2 and some of part 3, but I really need a lot of help to complete step 2 and 3. It's in process, but I need your help to complete step 2 and 3. And if you're interested in how does this C++ algebra look like? Well, they are very much analogous to C++ concept, which is another big feature in C++ 20. But essentially, you take a step back and look at how things are structured. For example, if you take a declaration is a specification of a type for a name in a scope with some initializers, right? When you look at it, you say, well, what is a type? Well, a type is, has basic type, and I can compose new type of basic type like pointers. I can say star int, and that becomes pointer to int. But then if I say arrays to the array of ints and 5, then I say that I have a type int, and I have an expression 5. So a type is the algebra. It's combined of the algebra of type and expression. And statement, you can have declarations, and you have expressions, types, and directives and attributes. So you see that when you start with this the hierarchy: type, declaration, type, names, expressions, and directives, and attributes, then you have some kind of cycle in there. But it's really important to tease those cycles out and have a sense of how they relate to each other, right? So if you, for example, if you're trying to parse a declaration, you need to know how to parse a declaration, but then you also need to know how to parse a type, an expression, a statement, which can itself contain a declaration and so forth. So that gives you a high-level view of the structure that you need. So the product of that, the outcome of that project, which is to have a uniform, simple specification of data structures capable of representing all of C++, not during enough to present all of C++, is what I call IFC. IFC is the format that the MSVC toolset uses to represent modules interface in binary form. So this project is open to the community. It's on GitHub. You can check the link there. You can use it. It has a very permissive license. You can use it as you see fit. The only thing you need to say is give credit. And of course, when you use it, you're very happy with it, please contribute so that the rest of the community can benefit from your work, and together, when we contribute, the project grows bigger, and the rewards, the outcome is not just the sum of each individual, but it's much bigger. Okay, so in short, an IFC file is just some kind of binary format today used by the MSVC toolset to represent metadata. And when you compile a module interface, or you want to turn a header file into what we call header unit, which is that you just pretend that header file forms a self-contained entity in its own, and you want to have the representation, the semantics of that, you save that in binary format. And the structure of it, as I said earlier, is based on the IPR project, which is something, which is a project I worked on with Piane. It is exceedingly simple to process. Like, you do not need a C++ compiler. Once you get your hands on the IFC file, you do not need a C++ compiler to process it. You can just write a very dumb script in Ruby, Python, or any other scripting language that if you just, of course, you can also write a program in C++, but it is not required. Or you can even, write it in JavaScript and view in a browser. And it's wonderful. So what do you find in an IFC file? Well, you have declarations, you have types, you have statements, expression names, everything that you see in C++, right? And then when you double click on those general categories, you see that, well, you also need to be able to represent strings. It's lower level source locations, because you need this kind of mapping between input source file and the semantics representation. You need token streams, because guess what? You have attributes, you have a bunch of other stuff that are just token streams. And you need to represent macros, especially to handle header units, and I call them preprocessing forms. And then you have a bunch of other, stuff that called heaps, just a blob of stuff. And you have some look-aside tables to deal with specific compiler extensions. Like, if I'm dealing with GCC, how should I interpret certain sequence of abstract references? The same goes for MSVC and so forth. Sometimes you need to save the internal states of the compiler so that you can resume it later, especially when you're dealing something you need to to do when you're dealing with anything with the preprocessor, right? Macro expansions and warnings, that kind of stuff. Now, the end goal is that we have all of ISO C++ and beyond, because we need to be able to represent extensions. The way we deal with this, to have simplicity, is that it's very hard to beat tables. So we start with homogeneous tables, arrays, and we call them partitions. So we have a bunch of data in homogeneous arrays, and then we refer to those the entries of the partitions by abstract references. And every abstract reference is a 32-bit value. And there is a portion that's a tag, and there's a portion that's an index into a partition. So when you get an abstract reference, if you know the tag and you know the index, you're good to go and fetch the entity that you're referring to. So concretely, an IFC file, this is how it looks like. You have the 4 bytes, that's just sequence of byte, signature that tells you that this is an IFC file. You're supposed to interpret this file, binary file, as an IFC file. And then you have a certain number of bytes that are called a header that describes how to find various information in there. It has a, for example, pointer to the table of contents that describes where to find specific things, and then that's followed by partitions. Remember, partitions are just homogeneous sequences of entities, all of the same type. And like I said, a partition is just a homogeneous table. It has a name, so you can say, oh, this is the declaration of classes, or this is a variable declaration, or this is a function declaration. So it's a name. We have string you can use to refer to partitions, and you have a 4 bytes integer that tell you where to find that partition from certain positions from the beginning of the file, and how many elements, entries there are in that partition, and each partition, what's the size of essentially how many bytes each entity in each entry in that partition occupies. And of course, like I said earlier, an abstract reference is essentially 32-bit value. We have a tag and then have an index. The tag is the thing that allows you to look up the partition that you need to look at, and the slot is given by the index. And it is quite simple. You can think of this abstract reference as some kind of strongly typed pointers. This is not voice star. This is a different kind of pointers and well structured and typed. So remember, when you take an IFC file, the 4 bytes just tells you this is an IFC file, and then you need to look at the header of the file, to get a sense of how to interpret the file. So you have a checksum, which is just some kind of hash of the content that you can look at to make sure that the file is not obviously tampered with. Here, say obviously, this is just a quick check. It is not a thorough, complete, safe check. But most of the time, if the check is, it's quick. If the checksum doesn't match, something wrong happened. So you have the versions of the IFC format. This is something that we evolving with the community. So we'll have several versions of the IFC. You have an indication of the ABI for which this IFC file has been produced, and which architecture, and also which version of the language. Is it C++ 11, 14, 17, 20, 23, or 2025? We don't know. And then the next thing that's very important is the string table. Remember, each partition is named. The way you look them up is truly a name, right? So you quickly need to know where to find the names, and all the names, strings, everything is something called the string table, just a huge array of characters, all the characters that appear in the source code in some form. And then you have a description of the the translation unit. Is it a primary interface? Is it a partition interface? Is it an internal interface? Is it a header unit? And also the path to the source file that was used to create the IFC file. And then, start the fun, which is that you have an index into the first declaration in the global scope. Everything starts from global. All declarations are written in the global scope. So get an index into the scope, and then from there you can start fetching all the declarations that you're interested in. Of course, you want to know where is the table of content. Table of content describes the partitions and where they are and so forth. So because C++ is complex, it's clear that you have a bunch of entities. You have declarations, that gives you a declaration index. Type, you have types, expressions, names, charts. So these are parameter list. You have strings, and then you have preprocessor forms, and then in scope, and then you have string literals, right? And then you have tokens, and then sequence of tokens. Sequence of tokens are just sentences, right? It's how things work. So once you've known these things are possible. So this is not science fiction. This has been shipping in at least in MSVC compiler for a while now. And the spec, you can find the spec on GitHub, the link I provided earlier. So once you have these informations, what is next? Well, what I really like to see is that the entire C++ community rally to collaborate for the C++ community to define this representation. Okay, if someone comes tomorrow with a much better representation of IFC, I'll be first to jump on it. Like, I'm not particularly attached to this one. What I'm attached to is the idea that we have a common representation, not common representation to Windows developers only, but common representation to the entire C++ community. It's together that we thrive, okay? So we have to start from somewhere. That's why I'm putting the IFC project forward. And the development is in the open, open an issue, start a conversation, and let's have that. And there are libraries out there like the IPR that are trying to create data structures, in-memory data structure from the on-disk representation. And in a previous talk by Sonny, you heard him talking about desire of having uniform experience of static analysis across all platforms. So if we can have something like the IFC, then and your compiler GCC is able to produce an IFC, and then you can just load it in a Clang tidy, and then run your Clang tidy analysis. Or conversely, or it could be MSVC. Not all these three compilers have the same analysis, but if you have a shared notation, just like we have a shared notation for C++ program, a sequence of characters, if we can have a shared notation of a much better representation, we can share a lot as a community around regarding the tool set. So I say a final call to action. What I would like to do is please go to GitHub, github.com, Microsoft IFC spec.git. Clone it, build it, look at it, find all the bugs, find all the things that are wrong with it, file issues, start conversations, so we can make it better. Okay, and if you want to play with it, you can also clone the IPR library, and you can start building IFC data structures out of the IFC. You can use today the MSVC toolset to produce IFC, and then you can write your own library or start a project to get an IPR library. Parser that builds IPR data structures from the IFC. Or it could be your own data structure. That is also fine. But let's do this thing together. Let's have fun together. Okay. And of course, I need your help for this thing to actually succeed. I need you to go and talk to your C++ developer tools providers so they do something about the IFC or do something similar to the IFC, but something common. so that we can all share the wisdoms that we develop through, programming in C++. With that said, I'm ready to take questions.
Thanks so much. Yeah, I definitely echo that call for people to get involved, and that this needs to be something which happens like across the community and across vendors, and so that we can all benefit from it the best we can. So we've got about 5 minutes left. We're pretty much straight on time. So we've got time for questions. If anyone would like to ask questions to Gabby, or I don't know if we have all the other speakers, but if anyone has any questions about any of the other talks as well, we can either get them up, or we can forward the questions onto them for them to answer offline on Twitter or something like that.
So are the questions on Elon TV or on StreamYard?
There will be. I have the technology. I'll let you know if there are any questions. I don't see any right now.
Everybody's ready for lunch, dinner, or something?
Yeah, that's good. I do have Marshmallow has woken up and was on my lap earlier watching all of the talks very, very intently. All right, not seeing any questions, so I think at that I'll say thanks very much, Gabby, for your talk.
Thank you.
Okay, and with that, we're going to close out. Thank you very much to everyone who joined in from whatever platform. Very much appreciated. I hope you all enjoyed the conference. If you would like to watch the sessions, they will be available on demand, both on Learn TV later and I believe on YouTube. So you can check those out later if you'd like to reference anything or send them to your friends, things like that. We also still have a bunch of pre-conference sessions, which are also on Learn TV and YouTube, which you can check out. We have, I believe, 10 talks on everywhere from MSVC update for C++20 and C++23. You can check out aka.ms/purevirtualcpp/on-demand to find all of that content. And I hope to run this again next year, so I hope we'll see you all there, and thank you very much.